Okay, let's start. Today we will discuss about the electromagnetic wave equation. In the last lesson, we have discussed on just the wave equation itself, and today we will specifically discuss the electromagnetic wave equation and also its solution. Well, um, we will show that Maxwell's equations result in general in wave equations. Okay, if we try to analyze Maxwell's equations, as a result, at the end we will get wave equations. Two types of equations will be discussed. First is source-free wave equation. Source-free wave equation means there is, for example, there is no current densities and there are no charges. This means source-free equations. We will discuss first source-free wave equation, which is also called a homogeneous wave equation. And the second equation is complete equation, which also include source terms, where J and Q are not zero, and complete equation called non-homogeneous equation, non-homogeneous wave equation. Well, first we will analyze our equations in time domain, but most of the work in this chapter and in the following chapters will be in terms of phasors and time harmonic wave equation. Okay, let's start first with a time dependent wave equation. Okay. Time dependent wave equation. Okay. So how do we know that Maxwell's equations in fact represent wave equations? Well, let's recall that wave equation was in the form that d square y dt square was equal to velocity squared d square y over dx squared. This was the wave equation itself. And how do we know that Maxwell's equations in fact represent wave equations? And the hint to the answer is the wave equation itself. And if we rewrite Maxwell's equations, we may rewrite Maxwell's equations in this form, in the wave equation form. We can rewrite Maxwell's equations in this form. Now we will see how, for example, how to rewrite Maxwell's equations in terms of magnetic vector potential. So if we write Maxwell's equations in terms of vector potential, if you remember, the Laplacian of magnetic vector potential was equal to minus mu j plus mu epsilon d squared a over dt squared. And the Laplacian of A, so the Laplacian of A, in fact, so this is, in fact, is the second derivative of A in terms of in the x coordinate plus second derivative of A in y coordinate and plus the second derivative of A in z coordinate, which is equal to minus mu j plus mu epsilon d squared a over dt squared. Okay, if we look to the wave equation and to the Maxwell equation which we wrote in terms of magnetic vector potential, we can see that both of them are in the same form. In other words, this equation which we wrote here is in the same form as wave equation with one exception, that here if we look to y, here y varies or varies in the x, only in the x direction. In our case, A varies on x direction, on y, and on z direction, and from the other side, y varies over time. Okay, this term is 1 over v squared, which is also present here, and this term is source term, which means, okay, which is and this equation called this equation is non-homogeneous wave equation, because if there exists source term, we said that our equation will become, or our equation is non-homogeneous, non-homogeneous, and much more general expression of wave equation than this, than the first, and more general. And if we want to obtain homogeneous equation, or in other words, if we uh, if we say that there is no source term, or if source doesn't exist, then the equation will be in the form where d squared a over dx squared plus d squared a over dy squared plus d squared a over dz squared will be equal. Okay, no source, no. When we say no source exists, we said okay, j will be 0, or the charge will be 0. In this case, j, if j is 0, this equation will become d square a over dx square d square a over dy square plus d square a dz square is equal to mu epsilon d squared a over dt squared. And this is called homogeneous wave equation for magnetic vector potential. Homogeneous wave equation for magnetic vector potential, or magnetic vector potential. Yep. Okay, we derived, well, it was not so complicated. We derived from the Maxwell's equation here, wave, from this Maxwell equation we derived the wave equation. First we derived non-homogeneous wave equation, and if there is no source term, we will derive a homogeneous wave equation. Okay, now let's see an example, a very little example. Okay, obtain a wave equation in terms of the electric scalar potential V. Can you do this, or let's let's see, and the next example you will try to do by yourself. Okay, how we can obtain wave equation in terms of electric scalar potential. We may start with Faraday's law, or if we look to Maxwell's equations, this is the first equation of Maxwell's equations. Okay. Faraday's law states that a rotor of electric field E equals to minus dB over dt, which is in turn equal to minus d. Well, B was equal to the rotor of magnetic vector potential. And since the operator nabla or operator del is independent of time, we can write in this manner that the rotor of dA divided by dt. Okay, now we take this term and move it to the left hand side of our equation. What we get? We get a rotor of electric field intensity plus rotor of dA over dt is equal to 0, or if we write in this manner, rotor of electric field plus dA over dt will be equal to 0. And okay, okay, and from the previous lessons we have seen that from this expression we may conclude that vector field, which is electric field intensity plus dA over dt, can be written as the gradient of some scalar potential. In our case, the electric scalar potential, but with minus. Don't forget about this minus. And so we may write that, okay, electric field intensity we may write as dA minus dA over the dt minus the gradient of V and now we recall Maxwell's third equation. Okay. Let me move this one also. Okay. What was the Maxwell's third equation? It was saying that divergence of electric flux density is equal to the volumetric charge density. And from here, we know that D is equal to epsilon multiplied by electric field. And it means that epsilon multiplied by divergence of electric field will be equal to, here the expression for electric field, the divergence of minus dA over dt minus gradient of V, which is equal to rho V. Okay. Okay, now let's move to a new page. Okay, we may not copy, we need to copy in. Okay. So, we are here. And now, what can we do? We may move epsilon here. Okay, it is obvious, and we multiply operator del to inside the bracket. It means that the divergence of dA dt minus the divergence of gradient of V is equal to rho V over epsilon. Now, we multiply both sides by -1. Well, we multiply both sides by -1. And we get, so the time derivative of the divergence of A plus the Laplacian of V is equal to minus rho V over epsilon. And now here the we applied the Lorentz condition, which is, I will write here the Lorentz condition, divergence of A equal to minus mu epsilon by, so minus mu epsilon by dv over dt, dv over dt. And if we apply this here in our equation, what we get? We get the Laplacian of v plus so we put it here, we get minus mu epsilon no wait, we get first, we have here d dt multiplied now minus mu epsilon dA over dt, which is equal to, so Laplacian of A minus mu epsilon d squared A over dt squared. So, okay, let me scale down this a bit. Why dA? Yeah, you are right. Not dA, but dV. You are right. My fault. Yes, you are right. Mu epsilon dV over dt, and here also mu epsilon d squared V over dt. Okay, great. And all this equal to rho v minus rho v, sorry, minus rho v over epsilon. So, okay. If, okay, here we obtained the, wait, here is V, here is also V. Look, here was V, here is also V, should be V. Why did I write here A? I don't know. And finally, we get the, I will rewrite one more time, mu epsilon d squared V over dt squared is equal to minus rho V over epsilon. Finally, we here derived the wave equation in terms of the electric scalar potential V. And okay, let me write in the new page. If there is no source, we will obtain homogeneous equation, which is minus mu epsilon d squared v over d squared, which is equal to 0. This is homogeneous equation. Homogeneous equation there if there exists a source, which means rho v is not equal to 0, we get the equation in the previous page, which is non-homogeneous wave equation in terms of scalar potential V. Non-homogeneous. If rho isn't equal to 0, yes. Yeah. You are right. If rho v is not equal to 0, it means if there exists some charge, we will get a non-homogeneous equation. And okay, you may take a note only these two as wave equations in terms of electric scalar potential V. Okay. Okay,